Hello, in this video, I'm going to go over chemical mixture problems, which is application of the first order ODE. Here is the questions. A brine solution of salt flow at a constant rate of 6 liters per minute into a large tank that initially held 100 liters of pure water. So the 100 liter of pure water is in the tank, and then 6 liter of minute, that is the flow rate of the brine solution of salt comes in, and then 5 liter per minute, this is the flow rate out of the brine solution of salt. And the concentration of the solution is 0.4 kilogram per liter for the flow rate in. So the question is to figure out when will the concentration of salt in the tank reach 0.3 kilogram per liter. So we set x as the amount of salt in the tank at time t, and then using the conservation principle, we can build the differential equation dx dt equals 6 times 0.4 minus 5 times x over 100 plus t. So here dx dt is the infinitesimal rate of change of the amount of salt in the tank, and then 6 is the flow rate in, and then 0.4 is concentration, and the 5 is the flow rate out, and then x over 100 plus t is the concentration of the salt in the tank. Here, the reason that we got 100 plus t in the bottom of the fraction, because the flow rate in is 6 and then flow rate out 5. So the amount of water in the tank will be increased by 1 liter per minute. So that's why we got 100 plus t. And then rewriting that differential equation, then we get this x prime plus 5 over 100t times x equals 2.4. And then this is a linear equations. So you can use either the method of integrating factor or the method of separable. So I'm going to use the method of integrating factor. So this is a p of x, this is a p of t, this is a q of t. So to first we find the integrating factor. Mu of t gonna be e to the integral p, right? So here p is p of t is a 5 over 100t. So the computing this, we got e to the 5 times natural log absolute 100 plus t, right? But 100 plus t is t represent time, so 100 plus t is positive for any choice of t. So we don't need to put absolute value. So I'm gonna take it out, and then we can simplify this as this 100 plus t to the fifth power, right? And then x of t gonna be 1 over mu times the integral of q times mu and the plus c. So this is 1 over mu, and this is q, and then that's the integrating factors. So simplifying and taking integral and then simplifying these calculations, we'll get 0.4 times 100 plus t plus c times 100 plus t to the negative fifth power. And then using the initial condition, which is x of 0, 0. Why? Because initially the pure water has been held in the tank, right? So there was no the salt in the the water in the tank, so x of 0 must be 0. So then the substituting 0 into the t, then we get 40 plus c times 100 to the fifth power, which is 10 to negative 10th power. So that must be 0. Then solving this equation for c, then we get negative 40 times 10 to the 10th power, which is negative 4 times 10 to the 11th power. So that's not the answer. Okay, we just got a particular solution of integrated problems. So question is to find out when the the concentration will reach 0.3 kilogram per liter. So the concentration is the mass of substance divided by the volume of liquid, right? So, so here applying that here in this problem, we got x of t over 100 plus t, which is concentration of the salt in the tank. So this we'll find out t that this one reach 0.3 kilogram per liter because I just dropped the unit. And x of t, we just got it, right? Which is 0.4 times 100 plus t, and then minus 4 times 10 to the 11th power, which is c, we just got it here. And then 100 plus t to the negative 6th power over 100 plus t. So 100 plus t is a common factor. So factoring out, right, and then simplifying these fractions, we got this. And solving this equation for t, so then we get 4 times 10 to 12th power and minus 100. So approximately, I mean, converting this one as decimal expression, we got approximately 25.99.